We're going to look at the graphing linear functions using the average rate of change to identify linear functions. That's one thing people struggle with a little bit, so we're going to do some examples of that. We're going to determine whether a linear function is increasing, decreasing, or constant. And we're going to build linear models and verbal descriptions. That's word problems, everybody's favorite thing. So that's some of the stuff we're going to be looking at. Everything that we're talking about, though, in this section is a line. It's a linear function. 4.3, we're going to start getting into quadratic functions, which is going to be a little bit. All right, so first things first. A linear function is a function of the form f of x equals mx plus b. So it's in that form. That's the, anybody remember what we called that form? The one we were looking at was y equals mx plus b. Remember what that's called? Slope-intercept form. Remember, m is our slope, and b is our y-intercept. Oh, there we go. So the same thing is going to apply here. You got f of x is equal to mx plus b. M is going to be the slope, and b is going to be your y-intercept. Same exact thing, except instead of y, we're putting f of x, g of x, h of x, whatever of x you want to put. That's all there is. The domain. What do you think the domain of a linear function is going to be? Anybody know? Think back about your domain stuff we talked about on Wednesday last week or so. 3.1, 3.2. Yeah. Remember, the variable could be whatever it wants, negative infinity, positive infinity. Is there a variable in the denominator? No. It's just mx plus b. There's no denominator going on there with a variable in it. Is there a variable under even roots? No. So the domain of all your linear functions, negative infinity and positive infinity, all real. Any questions on that? Now the range is a little different. There's actually two ranges that can happen for a linear function. Anybody knows what it could be? The first one's easy. So you have a range where it's negative infinity to positive infinity, right? All the y values are taken up. So when it's a line, it keeps going. Yeah, but there's one type of line that will have a different range. What do you think that might be? A horizontal line. Yeah, exactly. Good. So if you have a horizontal line, its range is whatever b is. Because b is your y-intercept. So whatever that value is, that is the range. It's just a single value. So horizontal line is the only one with a different range.
So how would you write it? Would you write like, if 7 was the range, would you write negative infinity to 7? Or would you write 7?
So it's just 7, right? It wouldn't be 6, it wouldn't be 5, it wouldn't be negative 13 or anything. So let's call this, let's say this function is, let's call it h. Let's say this is h of x, right? The range of h would just be the set containing, in your case, 7. It would just be a set with one value in it, 7. You couldn't write it in interval notation because it's not an interval, right? It's just a single value. Any questions on that? Question I got for you is, what type of line is not a linear function? A vertical line. Why is it not a linear function? All the x values are going to be the same. Yep. So if you have a vertical line, boom, boom, boom. What does it fail? It fails a vertical line test, right? You draw a vertical line and intersect every single point on it. So a vertical line is not a linear function because it's not a function. you'd have one x value and infinite y values. So that one x value is mapped to infinite y values. So it's at least mapped to more than one. So yeah, so vertical lines are not linear functions. Horizontal lines are, and they have a range of a single value. So, any questions on that? All right. So if we're given a linear function like this, f of x is equal to negative 3x plus 7, we want to determine what is the domain, what is the range, and we want to graph it. How will we do that? Clean this up so we're not doing that all night. What do y'all think? To graph a line, what do we need? We can use a slope and what else? And a y-intercept, yeah? Anything else? So that'll work. We can use the slope at any other point, and we can also just use 2 points, right? What do they give us here? We know negative 3 is what? It's negative 3 over 1, but we would call that the what? The slope, yeah. And you said 7? What is 7? The y-intercept. So that means we have the point what? 0, 7. Yeah. X is 0, y is 7. That's the y-intercept. So we can plot that point 0, 7. This would be right here. And then what can we do?
Go down 3.
We can use the slope to find the next one, right? We're gonna go down 3. So 1, 2, 3. And we're gonna go where on the x? To the right. You want to apply the negative to either the y or the x if it's a single negative. So that means we're gonna have another point right there, which is gonna be what? 1, 4. And so that will be our y. You could also went up 3 and to the left 1. Then you put the negative on the 1 instead of the 3. You could have did that as well. Any questions on that? So this is kind of review my mind of what we already did, but it's good to think about or review. All right. What's the domain of my function? Yep, infinity positivity, all reals. Can be the domain for all your linear functions. What's the range? Just 2 options, right? It can either be all reals or it can be a single value. What do you think it's going to be in this situation? All reals. So this would be negative infinity, positive infinity. And there we go. Any questions on that? All right. That one's so similar. Okay, yeah, I know we should do it. Let's look at what the directions are. Sorry, one second. I just want you to move it over a little bit. It's laggy. All right, so here we got g of x, which is equal to negative 4x plus 3. They want to know what is the slope, what is the y-intercept, and what is the average rate of change. Let's start with slope. Is what? -4, right? All right, m is -4, so our slope is going to be -4. What is the y-intercept? Is 3 plus 3, so that's b. So y-intercept is going to be, let's say, 0, comma 3. Now, the average rate of change, what is that? Anybody know? What does the slope tell us? It tells us how it changes, right? And so if we have a slope of -4, what is the average rate that it changes? It's -4. That's all it is. Now, the average rate of change for a linear function is pretty simple because linear functions have the same slope throughout. If you go on to higher math, you may be dealing with an average rate of change of a function that's more complex, and that's a little bit different. But for a linear function, it's just the slope because the slope doesn't change. And last thing I want to talk about is interpreting the slope. So let's say the x value changes blank units for every blank units the y changes. So how much does the x value change whereas how much does the y value change? Like what's the ratio? Is what? You're close. So where would the 4 and 1 go? Which one's changing 4? Which one's changing 1? X would be 1, and then y would be 4. The only thing is that what? It's negative, right? So we gotta make one of them negative.
So would you say 1 to 4 instead of 4 to 1?
Yeah, I mean, it depends on how you're wording it, right? So if you're saying that y is changing and then x is changing, it'd be -4 to 1. If you say x is changing this much and y is changing this much, then it's 1 to -4. So it depends how it's written. But I just want you to be able to interpret it. Like, what does that slope mean? It means that x is changing 1 unit for every -4 units, y value changes. And you could make it -1 and +4. You know, you could apply the negative wherever you like. Any questions on that? And let's graph it. So we got a y-intercept of +3, 2, 3. And we got a slope of -4, so we'll go down 4. 1, 2, 3, 4. And to the right 1. And so this would be let me draw a straight line. Any questions on that? Let's see what we got going next. Okay. Yeah, I'll try this one then. Then we'll go over it. So we got f of x is equal to 1/4 x minus 2. And zoom in more. We want to know what is the slope. What is the y-intercept? And the average rate of change. And then graph it. All right, so what's the slope of this one? 1/4, yep. So that means that for every time the y value changes 1, what does the x value change? 4. Good. What's the y-intercept? -2, so that means it's the point what? 0.2. Very good. And what's the average rate of change? 1/4. Yep. Good. Any questions on finding that stuff? All right. And so to graph it, we got 0, -2, boom, boom. It's going to go up 1 for y and 4 for x. So 1, 2, 3, 4. That looks like that's going to be my point right there. And we draw a line through there. Ta-da. Any questions on that one? All right, I got one more for this type of stuff. We got a linear function, h of x is equal to 3. And once again, we want to know the slope, the y-intercept, and the average rate change. We can work this one together. Do y'all want to work on your own? I can do that. Then we'll do it. All right. So what's the slope of this one? 0. Yeah. Good. Because it's what kind of line? Horizontal line. So this is slope of 0. I mean, if you want to think about it a different way, if you're having trouble, basically this is written as h of x is equal to 0 x plus 3, right? And so your m there is 0. That'll help somebody struggling with it. What's going to be the y-intercept? It's going to be 3, so we got 0, 3. And what's the average rate of change? Once again, 0. Yep. And so to plot that one, it's the line where all the y values are 3. So it's got a point here, 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 whatever, across there. So it's just going to be a horizontal line. There we go. If you get a vertical line on one of these, you did something wrong because it's not a function. So pay attention to that, or you can use that to check yourself. Any questions on that? We call this a constant function, if I haven't said that before, because it's constantly the same value, right? It's a constant, it's 3. All right. One of the things about linear functions is that their rate of change is constant. The rate of change does not change throughout. When you're drawing a line, it doesn't do this and then do this and then do this, right? It doesn't change how it's increasing because that wouldn't be a line. So when you're looking to determine if some data points, some data values can be modeled with a linear function or are a linear function, what you want to make sure is that the slope remains the same. The average rate of change remains the same. The rate of change between the points remains the same. Because if they don't, then it's not a linear function, or it can't be modeled by a linear function. So if you're given some data points like we have here, we have an x of -2, a y of 13, an x of -1, a y of 10. We got an x of 0, a y of 7, x of 1, y is 4, x is 2, y is 1, and x is 3, y is -2. If we want to see if this can be represented as a linear function, then what we need to do is calculate the slope between all those different points. So we need to calculate the slope between this point and this point, which we're going to do the difference in y divided by the difference in x, and we get -3. If we do that for all of these, we get -3 each time. That means that this data can be represented as a linear function because the rate of change between each point is -3. Any question on that? Now there are, if you go into like some type of modeling stuff, and you may have heard it before, when they talk about like a least regression line, that's different. That's where you're trying to find a line that kind of fits the best between the points. This is when we're saying like this is absolutely a linear function. The points are all on the same line. So that's the difference there in case someone gets confused. Yeah, we talked about that already. So let's say we got this data here. We got ages and the maximum number of heartbeats. That's got to be, I don't know where that data comes from. Because their heartbeat's going down? Is that a resting heartbeat? I don't know. So, but we got the age as the x value. We got the y as the maximum number of heartbeats. How do we determine if this is a linear function? They gave us the x, y values here. First off, what do y'all think this is a linear function? You can kind of make a little educated guess, right? This is increasing by 10 each time, and this looks like it's increasing by what? It looks like it's decreasing, huh? 2.5, 2.5, 2.5, 2.5. It looks like it's will be, right? Now, sometimes they'll skip one. Like they wouldn't have the 50 here, and that's when it gets a little more difficult. So let's write this one out. I made this little chart right here because this is how I like to do. I didn't, their chart's got too much going on. So we got 20, we got 30, we got 40, we got 50, 60, and 70. And then it was what, 50, 47.5, 45, 42.5, 40, and 37.5. And so what we're going to do is take the 2050, the 3047.5, and figure out what's the slope between those two. I like to put these little lines here showing, okay, this is what I'm working with here. And so I'm going to do 50 minus 47.5 over 20 minus 30. Now, you can do 47.5 minus 50. It's just that the denominator would then need to be, anybody know? 30 minus 20, right? So whatever order you put them in, remember the same order pairs need to be over each other. And so that's going to give us what? 2.5 over negative 10. Is that right? There we go. And so 2.5 divided by negative 10. Let's put that as a fraction. You get negative 1/4. So for all, let's start it again. For this to be a linear function or represented as a linear function, we need all the slopes to be negative 1/4. If any of them is any different, then it's wrong. It's not a linear function. So if we do the next one and it's not negative 1/4, we can stop right there and be like, no, it's not. So let's continue on and see. So we're not going to do these two next, which is a mistake I often see. We're going to do these two next. We're going to do the 3047.5 and the 4045. So we're going to do 47.5 minus 45 over 30 minus 4, which is again going to be 2.5 over negative 10, which is negative 1. And we can continue that. Now we're going to do this one and this one. And so I always get these kind of slanted. That's why I'm trying to use different colors. And so we'll have 45 minus 42.5 over 50 minus 4. Oh, I messed that up. Wouldn't be 50 minus 40. It'd be 40 minus 50. So make sure you do them in the right order. And so once again, it's going to be 2.5 over negative 10. I mean, this was kind of elementary to see a little bit. And then now we're going to do these two. So that's going to be 42.5 minus 40 over 50 minus 60. And once again, we're going to get 2.5 over negative 10, which is negative 1/4. And then the last two, I don't have any room, so we're going to fit it in there. So it's going to be 40. Let's try that. 40 minus 37.5 over 60 minus 7, which is once again moving 2.5 over negative 10, which is negative. So since all the slopes were the same, they were constant throughout, that means that this is a linear function. If any of them had been like negative 2.2 over 5 or negative 1/3, no, it wouldn't be. But since they're all negative 1 over 4, it is. Any questions on that? Now, like I said, on ones like this, where it's just always increasing at the same amount, 10 each time here, I don't find those too difficult. But when they start changing this up, like if you didn't have the 31 here, it would be a little bit harder to see just straight away. And that's when I think this really comes into play. If you can kind of see it from the data, that's fine. When it's something simple like this, I think even the next one we're about to look at is pretty simple too. Yeah. Those are pretty easy to see. But like I said, if it starts skipping some data values, that's when I would say that you definitely want to do this just to make sure. All right. Any questions on that? Oh, is that it for this page? Yeah. So here we got another one. I always think that's a hockey puck. It's a petri dish. A strain of E. coli known as O397 Rec A441 is placed in a petri dish at 30 degrees Celsius and allowed to grow. The data shown in table 2 on this page are collected. The population is measured in grams. So they weigh the petri dish. They probably, I guess, subtracted the weight of the gel and the petri dish. Plot the order of pairs X, Y in a Cartesian plane and use the average rate of change to determine whether the function is linear. I think y'all know how to plot stuff, so we're not going to focus on that. We're going to focus on trying to figure out if this is linear or not. So, if I was given this problem and I looked at it, first thing I would notice is my X is increasing by 1 every time. It doesn't skip any values, 0, 1, 2, 3, 4, 5. And so I can really just look at my Y's and say, okay, well, how much did that increase? Well, that increased 0.03, right? Between those two. How much did it increase here? From 0.12 to 0.16. That's what? 0.04, right? And so right there, you can see, no, that is not going to be linear. If you keep doing it, it's what? This is 0.06, this is 0.07, and 0.10. So every time X is increasing by 1, the amount that Y is increasing is changing. That means that this is not a linear function. Okay. You can go back and do it the way that we talked about by doing the slope each time, but since this is increasing by 1, really you just got to look at what's going on there. If it didn't, if it was like 0, 1, 5, 7, but your x values, then yeah, I'd be like, okay, let's do it the old way, the long way, just to make sure. But if it's something simple like this, you just gotta look at what y is doing, because you know what x is doing, it's just going up by 1 each time. Any questions on that? It's all white place. All right. This is the last thing we're going to get to cover today. We want to determine whether a linear function is increasing, decreasing, or constant. Now, we talked about increasing, decreasing, constant. We looked at some graphs where they were increasing sometimes, they were constant sometimes, they were decreasing sometimes over different intervals. But since a line has the same slope, it can only be one of those. It can only be increasing all the time, it can only be constant all the time, or it could be decreasing all the time. It won't be changing. It's what we call monotonicity in mathematics. So a linear function f of x is equal to mx plus b is increasing over its domain if its slope m is positive, is decreasing over its domain if its slope m is negative, and it is constant over its domain if its slope is 0, which means it's a what kind of line? Horizontal line, yes. Good. So if we look at these, we got f of x is equal to 5x minus 2. Is that line increasing, decreasing, constant? It's increasing. The slope is what? 5. It's positive 5, so that means it's going to increase with positive 5 slope. This one is increasing. Any questions on that? B, we got g of x is equal to negative 2x plus 8. Increasing, decreasing, or constant? Decreasing. Slope is negative 2. It's negative, decreasing. Any questions on B? C, got 3/4 t minus 4. Is that one increasing, decreasing, or constant? Why do you say decreasing? Increasing. Okay, why do you say increasing?
Because the slope is still positive.
The slope is still positive. It's a small number. It's 3/4, so it's less than 1, but it's still a positive number. So this is increasing. And D, we got h of z is equal to 7. Now it's going to be constant. It is a horizontal line. You can think of it as 0x plus 7, and so the slope is 0. That's a constant function.